distinguished Professor Yuval Peres, who is going to talk about geometry of area allocation to random points.
Okay. Good afternoon. I do have a request. So part of the lecture focuses on looking at some details on pictures. So if those in the back would be willing to move to some, there are open seats in the front, that would be much more effective. Okay, let's got it. And a large part of this work is joined with Nina Holden, now at NYU, and Alex Jai, who was at Stanford when we did this. But I'll also present works by and with many others in this kind of survey. And so please let me know if there are questions. The kind of questions we are looking at are really motivated by matching questions, but they are, in the end, instead of matching points to points, we will be matching points to domains. But first, this is also a good perspective. Here are two pictures due to Andor Holroyd that compare. We have several hundred points here, maybe 300 reds and 300 blues. And on the right, you see the optimal matching that minimizes the sum of the lengths between the reds and blues that are matched. Okay, so that's what you see here. Yeah, so that's what you see here. And there is a famous method called the Hungarian method to find this pretty efficiently, complexity n cubed. On the left, you see the unique stable matching of these points. So the points are in the same position. It's the same collection of points. So this has several equivalent characterizations. We call it the stable matching, but it's also the greedy matching. So you can get it as follows. Take the two blues and reds that are closest. So the blue point and red point that are closest, match them, take them out of the game, and repeat. And so you greedily match the closest pairs, and you get this configuration. But it's also the unique stable matching. So I'll say this in a future slide, but let me just say this in words now. A pair, a blue and red point that are not matched are called unstable if they are closer to each other than to their respective matches. Okay, so if I have, so think of blues and reds are agents, men and women, buyers and sellers. So every blue wants to match with one red, and every red wants to match with one blue that is as close as possible to it. So if we look at some matching, if there's a blue and red that are not matched, but each one says, oh, this red is closer to me than my official match, and the red says the same, this blue is closer to me than an official match, they will just break this official match and match together. So this is an instability. So if we require stability, it turns out in this setting, there is only one stable matching, which is the one obtained by the greedy algorithm I described in the beginning. So this one globally is less efficient in the sense that the sum of the matching edges, the length of the matching edges will be larger. And you see here also that on the left, you have some crossing edges. On the right, you cannot. Okay. Yes, of course, the distance depends on the topology, and we will discuss this both in the setting of the torus and the setting of the sphere. The exact matching depends on them, but the basic asymptotics we'll be concerned with will be the same. Okay. So, and I'm just referring to this 1962 paper by Gale and Shapley that considered this problem, also matching colleges to students. And in fact, this kind of stable matching arises in the way residents are matched to hospitals in the US and in many other places. I won't discuss. They described a nice algorithm to construct a stable matching. I won't get into that, but this motivates some of the arguments we use. Now, instead of matching, we're going to look at allocations, and this can be on the sphere, on a torus, also in infinite volume. But in this picture, I'm talking about the sphere. So take a sphere and let's make it have total area n, and then we have a set of centers or stars that are exactly n points, and we want to allocate to each one a unit of area in a nice or covariant way. So that, for instance, if these points are going to spin on the sphere, then the domains allocated to them should spin with them. And this, so formally, you can think of this as a map from the sphere to these centers, where the preimage of every center will have exactly the same area. Okay. Now, this is the first type of fair allocation that we studied. This was first with Andrew Holroyd, then with Chris Hoffman, Oded Schramm, Robin Pimentel, and we studied this in some detail. So what you see here is a fair allocation. In this picture, it's on the torus, but this actually works also in infinite volume in any dimension. So what is the method here? We start with these centers. So we have these centers or stars that you see here, these points. Informally, how do we assign them regions? Each one starts growing a ball at unit speed. So the radius grows at unit speed, and it acquires, the center acquires all the area it reaches first until it is sated. So it has a quota, in this case, a quota of 1. So we are choosing it so the area, say, of this torus is exactly n, and we have n centers. Okay, so we're trying to match to each center a unit of area. So each center knows its quota of a unit, and it grows a ball around it, capturing all the area it reaches first until it achieves its quota. Now, some centers are lucky, like this one, and it just achieves its quota nearby. But some centers are less lucky, and they have to go quite far. Like, look at this center. It tries to grow a ball around it, but remember, every point acquires every center acquires the points it reaches first. So this one that is hemmed in, it's not acquiring very much area nearby. So, but this keeps growing in the background until here it comes up for air and it acquires more area. And eventually everyone will be sated and everyone will get exactly their quota of 1 unit. Okay, but the drawback is the regions associated to the centers with this algorithm are not connected. So each one gets territory, but this territory need not be connected. And one advantage, this algorithm works in finite volume, also in infinite volume. If you start, the centers are not random points on a torus, but Poisson point process in Euclidean space. If it has intensity 1, then you can still do this and get area 1 or volume 1 for each center. This requires more work to prove. And in fact, a little bit of thinking will tell you that this model will actually yield a stable allocation. So that means if I look at the center and an ordinary point and ask, suppose that this point is not in the region, in the territory of the center, we cannot have an instability. So again, an instability would be a center and a point that's not allocated to it that prefer each other to their, to their assigned areas. So what does that mean here in the case of an allocation? So it means that an instability would be for a point, it's easy. For a point encounters an instability if the center it's allocated to is further than some center that it would like to match. But for the center, it means that this point that would like to match to it is closer than some points that it is matched to. So that would be an instability. And this ball growing procedure is in fact the unique one that gives a stable allocation. So this is stable, and it's the unique one. In the general setting of Gale and Shapley, they allowed for arbitrary preference orderings. And in that setting, the stable matching or allocation is not unique. So there are several different ones in general. But when the preferences are determined by a metric, and it's the same metric for both sides, it turns out easy to prove that it's unique. Again, everything is more involved in infinite volume, but this does work also in infinite volume. Yes. Yes. Sure. Yes. Yes.
Ball growth criteria is essentially the same as the stable allocation for only the points.
No, because it looks in all directions. So the stability, when I compare, if this is an instability, I'm not just looking along the same radius, but I'm comparing in all directions.
What I don't understand is that in the previous slide,
sorry, let me go.
Like, why is it that this thing that you mentioned, the center goes all the way far away? The other one, not this one. For example, the orange circle.
Yeah. Here. Oh, the previous slide? Yeah.
What's this one?
Yeah, this one, yeah. So it keeps growing. To where? So you're looking at this one? And compared to this one? So you see, the area near here, this is all captured first by this center. So there is no instability here. If you look at any point here, it doesn't prefer this center to this one.
What guarantees that the orange one goes all the way to that far down?
Well, so the orange one, it keeps, so the ball growing procedure, the ball keeps growing in the background and acquires all the area it reaches first. Now, because we have planned it so the total area is n, and every and every center has a quota of 1, then once then if a center is not sated, there is some area out there which is still not allocated. So it will eventually reach it. Well, I mean, we can go over this more at the end. So absolutely, it's very close to Borna, and I'll maybe you'll see one connection here, and I even had some slides with Voronoi. So the way to connect to the Voronoi is consider another parameter alpha, which is the appetite. So to get this allocation, we took every center had appetite 1, but you could think of the appetite as a parameter, and here is where the quota of every center will be alpha instead of 1. And here is a picture with 0.2. Here's a picture with 0.8, and here is a picture with 1.2. And if you make the appetite infinite, you'll get exactly the Voronoi tessellation. So, of course, because every center will reach all the points that are closest to it. So, at first, you would think that the higher the appetite of all the centers, the more chaotic the picture will be, but that's not the case. In fact, the picture is, there is exponential tails to how far you need to go for all non-critical models. So the most chaotic is the critical one, alpha equals 1, and the smoothest are, well, in alpha equals 0, you just get the original points. In alpha equals infinity, you get the Voronoi tessellation. So all the boundaries are just polygons. So, and in all those cases, we can show that a point doesn't have to go very far to find its domain. So there are exponential tails, but the tails are polynomial for the critical case, and that's also the only case where we don't have an exact estimate for how big the tails are. So that's a subject, of study, but I'm going to continue and tell you about another method of allocation. And again, some of you have heard about this. Another one that we studied with other co-authors later, and this appeared in the notices of AMS. This is gravitational allocation. So here, so again, we're going to jump over the generalities and tell you what is this rule. So somehow we have something here that is disturbing the slide. Okay, so what is the gravitational allocation? Again, some of you who have been in Sanya may have seen this. So we use a different method. We start with the logarithmic potential, which is exactly the radial harmonic function in 2 dimensions, but we're going to apply it in 3 dimensions. And so this is the logarithmic potential, and the potential applying at every point x will be the sum of the potentials from all the stars. So L is the set of stars or centers, and this is the potential at every point. And the force acting on every point will be the spherical gradient of the potential. So informally, what you should think of is that every star applies a 2-dimensional gravity force. So the gravity force is inverse proportional to distance, and every point feels the sum of the gravity forces from all the stars. And it will move in the gradient flow according to these, the sum of these forces. And almost every point, it turns out, moves along a path and gets swallowed by one of the stars. So there's a set of measure 0 on the boundaries that are undecisive points, but except for them, almost every point gets swallowed by one of the stars. But okay, so you get a picture like the one you see there. Maybe this light could be turned off. So you get the picture where, like you see there, of territories or basins of attraction to every star. Now, right. Somehow working. Okay. So formally, we have this basin of attraction, and for every point, every starting point x moves according to a gradient flow, which is this given by this differential equation. So the dy dt, this path starting at x, dy dt is the force. This is this gradient, the force applied to the current location. We start at x, and except for measure 0, we end at one of the stars, and that's exactly how far this differential equation has a solution. Okay, any questions on this picture? Here's another way to think of this model. This is a picture of a little subregion and on the sphere, and the potential, a graph of the potential on this region. And then you can think of, at every point, put a pebble and see where it will roll. That's the basin of attraction of the relevant singularity. So the potential is -infinity at every star, and we're doing gradient descent into these stars. Okay, so I'll go quickly, but when the key point, let me go back, is that here, remember in the stable allocation, we built in the quota of 1 to every star. It just, when it reached a unit of area, it stopped. Here, amazingly, it's just basic potential theory implies that without putting in this quote explicitly, it exists. So the territory for every star will have exactly the same area. And I'll just illustrate some examples. A few years back, I was giving a lecture on this in Montreal, in the conference of the Americas, and the organizer was very diligent. He said, "I don't believe your theorem, and before I publish the abstract, you should convince me." So he sent us this picture. Well, what if the stars are located all, close to the North Pole? Then surely, if there's also a star on the North Pole, it won't get the same area because it's surrounded. And so we sent him back the picture of what happens. So in fact, all the areas are the same, and there are some particles from far away, some that go to the center because the forces from the other points exactly balance. He said, okay, I understand this example, but what about this example? If there's, say, a star in the South Pole, and all the other stars are in the North Pole. Here there are 4, but think of 1,000,000 stars, in the Northern Hemisphere. Surely this lonely one on the bottom will get a larger territory. And, this is the picture we sent him back. So the point is, it doesn't. And when you have a lot of stars in the Northern Hemisphere, they gang up together and pull points that are close to the South Pole, still get pulled to the North Pole. So things magically always exactly balance. And the proof that you get exactly unit area is a beautiful 5-minute application of the divergence theorem. I see we end at 5:30 or 5:35 maybe?
17.
Okay, so that's the one calculation I want to show, then we'll go back to pictures. So, so apply the divergence theorem on the sphere with respect to this, first to this potential. So remember, U, the potential, was the sum of the logs of distances from the stars to a given point. And we apply the divergence theorem on a single basin. So take a star Z0 and look at the basin of Z0. Okay, you need some theorem from differential equations to know that the basin will have piecewise smooth boundary. And then we apply the divergence theorem there. And it tells us that, so if we take the force, remember the force was minus the spherical gradient of the potential. So we apply the divergence to that, we would get minus the spherical Laplacian of the potential. So this is just, what you see here is just the divergence theorem applied on one basin. Now, here you have the force multiplied by, a dot product with the outward normal on the basin. But the boundary of the basin, on the boundary, the force is parallel to the boundary, because if a force would go into a basin, then this point would be attracted to one side or the other. So on the boundaries, the force is actually parallel to the boundary. And so the force times the normal this is actually 0 on the whole boundary. So the right-hand side turns out to be 0. What about the left-hand side? So if we were taking Laplacian of log in the plane, we would just get Dirac, just the Dirac function, so 0 except at the center. But because we're working on the sphere, there is a curvature correction, and it turns out that this spherical Laplacian of the log is what we would expect in the plane, 2 pi delta z minus 2 pi over the area of the sphere. So I'm going to take now a sphere of area A. Later we'll set A equals n, but now we just call it A. And so the spherical Laplacian of the potential is a sum of these terms. And because we know that the integral on the left-hand side equals the right-hand side, the integral of this has to be 0. We're just integrating over one basin. So there's only one star inside the basin. So when we integrate, this part will give us 2 pi. And this part will give us, the curvature correction will give us 2 pi n over A times the area we're integrating. So in the end, just from the divergence theorem, we get an equation that we can solve that says that the area of the basin will be exactly the total area over it. So I went through this a little fast, but There is a article, there's a short but still more detailed version of this in PNAS from a few years back. And then there's a full version of this work in Annals of Probability if you want to see more details. Okay, so the key thing we prove in the paper is a quantitative property of this allocation, namely that the typical distance and the average distance traveled by a point is going to be bounded by a constant root log n. Now, to remember the normalization, we're working on a sphere of area n now, so we want each center to be allocated the unit area. So this will be a sphere. This is a two-dimensional sphere embedded in 3 dimensions. Its area is n, so its radius is constant root n. And we're saying that, so this is a rather large radius, constant root n. We're saying that the distance traveled by a point does grow with n, but still it's much smaller than root n. It will be root log n, and up to the constant, this is sharp. So this is the average distance traveled. And here are some pictures illustrating this. So what this means is that, remember that these regions all have area 1 normalization, but the average distance traveled in this basin is root log n. So it means as n grows, these will get more and more elongated or salamander-like. And you see this in the picture. So this is n equals 200, this is n equals 750. So you see that these regions have to get more elongated because their areas stay 1, but the average distance traveled grows with n. It's quite surprising you can see root log n in the simulation because it's a slowly growing function, but actually we can see it. And there is an interesting history that I just will say 2 words about, that this type of analysis, the idea goes back, and I can't give all the background, but the most relevant background for us was a work of Nazarov, Sodin, and Volberg, where the centers were not uniformly random or Poisson points, but there were zeros of a random analytic function, and they didn't think of it in terms of gravitational potential. When you have an analytic function, there's a natural potential associated with the function, which is its logarithm. So they did a remarkable analysis of this case, and this was a guideline for all the later work. In higher dimensions, there's a paper in Annals of Math with Chatterjee, Ron Peled, and Dan Romick, which analyzes this in all of space. But it turns out the 2-dimensional case was the most interesting and delicate, so it was saved for last. And that there you have to work in finite volume. The process doesn't converge in the plane, it does converge in finite volume. So this root log n suggests that you have a problem when you drive n to infinity. In higher dimensions, the expected distance traveled stays bounded with n. So the shapes don't get more elongated. So the 2-dimensional case is the most delicate, which is well known in potential theory. 2-dimensional potential theory is trickier than higher dimensions. So this was the stable marriage allocation we've seen before. One can use the allocation to get a matching. So I'll just say this in very briefly. So suppose I know this allocation theorem and how far the allocation goes. How can I use it to get a matching now between n blue points and n red points? So a kind of gravitational matching. So here's how it goes. I'm going to have n blue points and n red points, but I first put down all the n blue points and I put them down in random locations. And now the red points are going to come in one by one. So the first red point comes in. It feels the force of the blue star. So now the blue, the stars are just the blue points, and they apply this gravity force. The red point will travel, and with probability 1, since its location is random, with probability 1, it will be matched to one of the blue points, but not necessarily the closest, the one that the gravity leads it to. So it will be matched. And then after it's matched, we remove the 2 and we repeat. So now we put in another red point and see with the remaining n-1 blue points, which one gravity will lead it to, and we repeat. And we can do this until the end, and in the end we get average distance of root log n, which is known from old work of Aitai, Komlos, and Tuznadi that it's optimal up to constant. So this yields an optimal matching scheme up to constant. Why can we analyze this as opposed to, you might want to do a similar thing with Voronoi cells. So the more natural thing to do in the first picture is, instead of using gravity, when I put the first red point, a more natural thing is to use greedy. So when I first put the first red point, just match it to the closest blue point instead of the gravity and remove. Why don't we do that? Well, you can do it. It seems to be, in the end, perform slightly less well, but we cannot analyze it. And why can we analyze this scheme? It's because of the equal area theorem. Because when we put the first point in, what is the chance that it will be allocated to each of the blue points? It's exactly the same, because it's just given by the areas of the bases. So when I put the first red point, I ask, which of the blue points will it land? It doesn't matter how the blue points are located. Each blue point will be matched to the incoming red point exactly with probability 1/n, because the areas of the basins are all the same. If I would use greedy matching, then the probabilities would be given by areas of Voronoi cells, which are not the same. And so after one step, I will get a configuration which is no longer random. When I put n uniform blue points and remove one of them uniformly at random, I will get n-1 uniform blue points. But if I have n blue points and I remove one of them looking at the geometry, like I remove one where the highest Voronoi cell has a higher probability, then after that, the distribution of the blue points has been distorted, and we can't analyze how the greedy one behaves. So that's one challenge, analyze any of the greedy algorithms. So the greedy algorithms are much simpler than this gravity, but harder to analyze. Okay, so that's the basis that why we can analyze this gravitational matching algorithm. There's a nice story, but I don't have really time for it, for why the distance of the matching is root log n. I'll say one word that's in this picture. It turns out that you can calculate the typical magnitude of the force acting on a point is order root log n, but that's kind of the global force acting on a point from all the stars. But there's also a local force. If a particle gets very close to a star, then there's a force which is inverse proportional to the distance. So it's a fight between global and local, and the particle will be swallowed when it reaches close enough to a star so that the local force from that star will dominate the global force affected by all the stars. And then you can see that it will have to travel until a distance of root log n, because you need a strip of width 1/root log n to accumulate about a unit of area before encountering such a star. So, sorry, but just 2 minutes, I'll have to skip this, and I'll end with 2 more pictures and one 30-second movie. So one can do this thing in any geometry, and if you move from the sphere to the torus, everything stays the same. It's more interesting thing would be to look at high genus. We haven't done that, and to look at hyperbolic geometry. This is work that was started but not quite completed by Jian Ding and Ron Pellet. So I'll just show you the pictures of what happens when you do apply the same ideas in the case situation with hyperbolic geometry. Very striking pictures. The analysis, they did a lot of work, but it's still, unpublished. So but I have the permission to show the pictures. And there are various open questions. The one I like the most is about, and I want to end with this 30-second movie. So let's see if we can do that. It's about electrostatic matching. So let's go there. So you see, gravitational matching, we had to do it one by one. We couldn't apply gravity. We couldn't put the n blue points, n red points, and apply gravity, because then we wouldn't get a matching. We would have several red points match, being attracted by the same blue point. However, if you use electrostatic matching, you will naturally get, you naturally get a matching. And let me see if we can get this movie going. Okay. Here. And they want a new share. Okay, and we want to restart this. Okay, so what you see here, we start with 100 blue points and 100 red points. When two get together, they become green. So that's how we get the green point. So I'll start the movie over so you can see what's going on. Okay, so each point feels attraction from the points from the other color. So each red point is attracted by the blue points with two-dimensional electrostatic force, so inverse proportional to distance, and it is repelled by points of the same color. Somebody's phone. Yeah. Okay, it's repelled by points of the same color, and so even though initially a blue will attract all the reds, once a single red matches to it, the charges cancel. So now this green point doesn't attract or repel anything, so points will pass right by it. And so we will get a matching from this. Okay, so as we go here, all the points eventually get matched. And this seems to perform quite well in practice in terms of the average distance of the matching, but we can't analyze it. The problem is that after the points start moving, all the points are moving, and even if we start them uniform, after a while the distribution is no longer uniform, so we can't understand the distribution of the overall force, and we're lost in this analysis. So that's one remaining challenge. What? For electrostatic, or what happens if you have a different number of red and blue? So that's so you will get so say you have 10 reds and 12 blues. Then the 10 reds will be matched to some 10 blues, and there will be 2 remaining blues that will just what? They will end. Yes. Where will the survivors? Yeah, who will stay on the island? So, yeah, that's another good question. So of course, these remaining 2 blues will stop moving because all the charges, they won't feel any remaining charges. Where they will, right? That's right. They will repel each other. So if we are, yeah, it'll stop moving. That's right. You're right. And if there are several, then they will move to some minimum energy position. Yeah, that's interesting. We have not thought of that. So thank you, and I can think about it some more. Thanks for your attention. there any more
Okay,
questions?
questions?
You have three different colors. I think that's, I agree with Sergio. It's not, I mean, anyway, we can discuss this later. Yes.
So can you use optimal transportation ideas from there?
Yeah, dynamics or probability theory. I don't understand.
Do we use real dynamics or probability theory? So,
Yes.
of course, in the analysis, we have to combine the two. But the way the process moves is by gradient flow. So note that it's not, so the force, Sergio, we'll discuss this after, if it's okay. I want to answer the question. So I emphasize that the movement is according to the gradient of the force. So the force acts to the gradient of the potential. So the force actually acts as the velocity. The force is not acting as an acceleration. So it's not Newtonian dynamics, something called Aristotelian dynamics, because so it's really gradient descent for the gravitational potential. You can think of a high viscosity situation if you want to model this physically, but the force is not giving acceleration, because then we would have stars, then we would have particles circling the stars, and that's not what we want. We want particles actually swallowed by the stars, and this happens when the force acts as a velocity. But with the force acting as a velocity, we do the exact correct dynamics for this, for this gradient flow.
Okay.
But thank you for this. If I have more time, I would emphasize this more. So thanks for asking.
Usually you can calculate effective curvature using the momentum principle, right? You can calculate effective curvature of this dynamical system. Then understand this is hyperbolicus dynamical system or something else, zero curvature and so on. This will help to understand how nature.
So maybe, oh, go ahead.
Then you have this quick equation for motional particles in this matrix. This is for special case of the matrix, also the Newton equation.
Okay, but as I said, here we don't get the Newton equation because the force acts as a velocity for the particles and not as this acceleration.
Or you asked Professor Yao, you had a question?
Yeah, I was wondering whether one can apply some idea from optimal transportation in the continuous case to deal with the discrete case.
So, sorry, I didn't hear the
Optimal transportation, the ideas.
Yes. So, right. So this is closely related to optimal transportation, where we are minimizing the square distance, and I skipped some slides on that. So we're minimizing the average of the square distance, and there are some works on that, but on seeing the gravitational allocation as a transportation that minimizes the average square distance.
Can one reduce it to continuous case by just spread out the points?
So for continuous case, here it's a mixture of discrete and continuous, right? We're matching, we have discrete endpoints that are matched to the continuous. So you want to do a completely continuous version?
Yeah. And then try to approximate the delta function by somehow.
Yes. So, yeah, there are some PDE papers that do that from 2016, 2020, and in the full version of the talk, I discussed these. But indeed, that's been been a direction that has been explored. And there's still more to do.
But you actually in the continuous case, we use a discrete version to achieve the continuous case. So I wonder whether we can use that. So you can try to approximate discrete by continuous version, and then in the continuous version, we actually devise some discrete approach.
Uh-huh.
So maybe it could be related to discrete version.
Okay.
This is in my paper with David Gu.
Uh-huh. You're looking at related questions there?
No, we do the continuous version of the optimal transportation. But when we did that, we use a discrete approximation.
Uh-huh. But are you optimizing W1 or W2?
Yeah, we optimize W1, I think. We can do that.
Okay, so gravitational allocation is certainly, it optimizes W1 up to a constant, but it doesn't optimize W1. We know that. There's lots of evidence that it's optimizing W2 asymptotically as the number of points grows.
Well, that should be interesting to compare, I think.
Yes, it needs to compare. So thank you. I will look at that.
Yeah.
Hello. Yeah.
Yes.
In the middle somewhere, you were saying something about zeros of holomorphic functions, and have you thought about applications to modular forms? Because I'm asking because there is a connection between the distribution of zeros of modular forms to the distribution of the mass of the modular form itself. And whatever you showed, at least the pictures looking at it, I was thinking about the converse. If you can show that the zeros are equidistributed in some sense, then can you show that the mass is also equidistributed? Something along those lines. Have you thought about applications to modular forms or even zeta functions for that matter?
I have not. I don't know of applications to modular forms. Again, the case that's been, besides the case of uniform random points, which I have focused on, again, Nazarov, Sodin, Volberg have studied the case of the zeros of a very special Gaussian analytic function. They're essentially a single function. So the coefficients are IID complex Gaussians divided by root n factorial, and the zeros of that form a translation invariant point process in the plane, and these points are much more rigid. They're closer to a lattice than to random points. You don't have big holes, and you don't have overcrowding like you would have with Poisson. And they represented this by very good behavior of the two-dimensional gravitational allocation, though they didn't use this name. They used allocation for a potential, which is essentially log of the absolute value of the relevant analytic function. But even though the process they were analyzing was very different, the ideas they introduced there have been crucial in all later related works. So this is Nazarov, Sodin, Volberg, an amazing team.
So I have two very naive questions. One is, if I replace the sphere with something piecewise a smooth surface, let's say a cube, rectangular cube, what happens? Especially your example with stars were located around the North Pole. So if I put that star in the very corner of the cube, then I cannot use that Green's theorem to find it. So.
Yes. So I admit I haven't thought about the non-smooth case, so I can't give an answer, right now. You can think or discuss.
Second question is, if you have it for the smooth case, it gives you this stratification of the surface.
Right.
Of course, it's based on area.
Yes.
Does this stratification tell you anything about magnitude homology or path homology of the surface? Because I can think of stars as vertices of the skeleton. The graph associated to the surface is discretization of the surface. And in some sense, it actually is based on not distance, but based on area. So maybe it tells us something about path homology of the surface.
I have no idea. So it would be nice to understand.
It would be actually pathomology of the skeleton of the cell somehow, not the surface itself. So that doesn't make sense. Any other questions?
So you
Yes,
had
Jacob?
some bound for when you had like endpoints on just thrown onto a two-sphere.
Yeah.
What happens to this kind of result if you project like stereographic projection to the plane? Do you still have some kind of nice bound or?
So I know that the same bound applies, say, to endpoints on the torus, but when you do stereographic projection, the image of the sphere is unbounded. So an area is not preserved. So yeah, I don't know. We can discuss it later. So it's very nice. So it's a different argument, but it still turns out to have equal area. So you yeah. So that's right. So in the sphere we use the curvature. In the torus, it's still true, but the argument is a little different that the regions have equal area. Yes. So let me say the underlying principle that goes back to Moser is that one effective method, it's not optimal transportation, but it's a very nice transportation. I have two measures and I want to transport between them. So the general principle is I do that by looking at the function whose distributional Laplacian is the difference of the two measures, and using gradient flow, so I find the potential whose distribution potential is the difference of the two measures you're trying to transport between, and use gradient flow according to that potential. So that's the principle, and to see that it works, you need some assumptions, but that's this principle that appeared certainly in Moser in 1990, may have even older roots. So these cases are cases of this principle, though you can't just appeal to the principle, you have to verify that in a specific case that it works.
Any other questions?
Yes. So that's what we did in the end. The electrostatic matching was based on stars of the same color repel. In the main discussion, the stars were not moving, right? The stars were in random locations, but they were fixed. And then the particles were attracted to them. So in the version I discussed at the movie at the very end, we had n blue points, n red points, and exactly the blue points repelled each other, and the red points repelled each other, and blues attracted red. So electrostatic potential. And so you saw the simulation, it seems to be, one can show it creates a matching with probability 1, but to analyze the distances typically traveled by this matching when you start with random points, we don't know how to do, because the key to the analysis in the gravitational case was the fact that the location of the stars was fixed and it was uniform, so we can analyze it. And even when we did matching, when we removed stars one by one, we always had uniform stars. So the points applying the force didn't move and their distribution was uniform. Once the points applying the force start moving and their dynamics doesn't preserve volume, then they have some strange distribution and we can't analyze it. the distribution of the force for these points, we can't analyze without knowing what's the distribution of the points. So that's a challenge.
Well, if no more questions, let's thank the speaker again.
Good talk.
What was it, Perez?
I said good talk.
Thank you.